This video marks the start of Chapter 7. So in Chapter 6, we sort of introduced the second law of thermodynamics and went over the concept of efficiency and coefficient performances for heat engines and refrigerators and heat pumps. In this case, we're going to be looking at how to apply a second law analysis on processes. So the first step in looking at this is going to be introducing the concept of the Clausius inequality. Now, when I taught this class years ago, I used to go over a full derivation of this, but sort of have condensed that down to a brief explanation because I believe a fuller explanation could be better understood once having gone through the material. So I'm just going to go ahead and introduce the concept. So basically, there's the Clausius theorem that states whenever a closed system undergoes a cyclic process, the cyclic integral dq over t is less than 0 for an irreversible cycle and equal to 0 for a reversible cycle. This inequality is a consequence of the second law of thermodynamics, where Q is the heat transfer to or from the system and T is the absolute temperature at the boundary. And the symbol, the integral sign with a circle around the center of it, is a cyclic integral. Now, in short, the conclusions associated with the Clausius inequality is that the inequality holds for a totally or just internally reversible cycle. The inequality in the Clausius inequality holds for irreversible cycles. So now consider other quantities that have the characteristic that their cyclic integral is 0. The cyclic integrals for heat and work are not 0. The change in any property after undergoing a cycle is 0, right? Because what you're doing is coming back to the start. So consider the change in volume of a piston cylinder device that undergoes a cycle, for example. So therefore, inequality whose cyclic integral is 0 depends only on the state and not on the process path, and is therefore a property. So all that basically to say that this quantity must represent a property, since if you go through a cycle, it comes back to the same point it started from and has the same value that it started at. So this property is what we designate as entropy. And the change in entropy, ds, ends up equaling 0 for a reversible cycle. So the term entropy is generally used to refer to both total entropy and entropy per mass, right? It's kind of like saying total internal energy and specific internal energy, right? Specific internal energy would be kilojoules per kilogram. Total internal energy would be, for example, in kilojoules. Well, it's the same thing. There's an extensive and then also an intensive per unit mass version of entropy. It follows that the change in entropy for a process can be found by integrating this quantity. So to use that above expression, the relationship between Q and T during a process must be known. Example, an internally reversible isothermal heat transfer process, you can actually quantify that. So this is for an internally reversible process. So the point is that what we're going to be heading for is being able to quantify changes in entropy for a process and eventually getting into whether or not the change in entropies are due to irreversibilities. We'll get there in a minute, but let's go ahead and do a quick example problem. During the isothermal heat addition process of a Carnot cycle, 900 kilojoules of heat is added to the working fluid from a source at 400 degrees Celsius. The entropy change of the working fluid, the entropy change. It says determine, sorry, the entropy change of the working fluid, the entropy change of the source, and the entropy change of the process. So what we have in this example problem is that we have heat being transferred from one point to another. And as that heat is being transferred, it carries with it an entropy that's quantified by this expression. So that is a term that we will later equate to called entropy transfer. As heat moves, so does entropy, right? I'm not talking about irreversibilities at this point. I'm just talking about the fact that when heat travels, it carries with it entropy. It's called an entropy transfer process, right? So it's saying I have an isothermal heat addition process that's happening. And during this isothermal heat transfer process, I have 900 kilojoules of heat being moved from one point to another from a source that's at 900 C, or 400 degrees Celsius. So it's asking us to find the change in entropy of the working fluid that's absorbing the heat and the change of entropy of the source that's giving up the heat. So as that heat travels, it carries with it entropy. So again, we can quantify this as the integral of Q over T, or dq over T, which ends up just becoming Q over T. So in this case, so if you're looking at A, we're trying to find the change in entropy of the fluid. Right, what we end up with is the heat leaving the source divided by, the heat being absorbed by the fluid divided by the temperature of the source from which heat is coming from. So that would be what I would quantify as the amount of entropy being transferred from the source to the water. So the source gives up 900 kilojoules of heat and is absorbed by the fluid, and the source is at 673 Kelvin because in this case the temperature needs to be an absolute. So we quantify that as the fact that 1.34 kilojoules per Kelvin, that's the unit for total entropy, kilojoules per Kelvin, was absorbed by the working fluid. So the source transferred heat, and also that heat carried with it entropy. It's kind of like thinking about mass, right? We have mass. In Chapter 5, we talked about energy transfer by mass, that when mass travels and goes over a boundary into a system, it carries with it enthalpy, kinetic energy, and potential energy. Well, the mass entropy, heat is sort of the same way, as it carries with it entropy from one point to another. So it's carrying entropy into the working fluid from the source by taking the amount of heat that the water absorbed that the working fluid absorbed divided by the temperature of the source from which it came. Then part B is asking, well, what's the change in entropy of the source? Well, that would be the heat leaving the source, which is negative Q, over the temperature of the source. So we get 900 kilojoules worth of heat that the source gave up, divided by the temperature of the source, which is 673 Kelvin. So the source lost 1.34 kilojoules per Kelvin worth of entropy. Then part C asks for the total entropy change of the process. Right? The total entropy of the change of the process would equal the entropy change of the fluid plus the entropy change of the source, both add together to be 0. So this is a reversible process because there was no total change in entropy due to there was no additional entropy produced. And we'll talk about that at a later time, but right now we're just looking at the entropy transfer term by heat. Okay. I hope that part is clear. We're gonna go ahead and continue to the increase of entropy principle. All right, so consider two processes that make up a cycle. Right, so we have process 1 to process 2, and then process 2 back to process 1. Process 1 to 2 is reversible or irreversible, let's say, and process 2 to 1 is internally reversible. If we go ahead, we apply the Clausius inequality to it. We have to apply the cyclic integral of Q over T, so we'll go ahead and do that. So we have the process 1 plus process 2, where process 2 is designated as reversible. Has to be less or equal to 0. If I continue that, I find that for process 1 to 2, my change in entropy has to be greater than equal to or greater than the Clausius inequality. Or I can also put this in differential form. So this inequality becomes an equality for internal reversible, and it becomes greater than for reversible. Basically, what this suggests is that some entropy is generated or created during an irreversible process. So this is another term that will eventually be brought into what we would call a second law analysis, and this term is called entropy generation. So let's go back and let's expand what we would call our second law analysis is the change in entropy during a process, right? The entropy at state 2 minus the entropy at state 1 has to equal, I would call this the entropy transfer by mass, or sorry, entropy transfer by heat, plus entropy generation, right? This is for a closed system. Now, let's talk about the difference between the first law analysis and a second law analysis, right? First law analysis, we say all energy in by heat, mass, and work minus all energy out by heat, mass, and work equals the total energy change of the system. What we're doing right now is building up what's called a second law analysis. Entropy, which is an entropy balance, right? We'll get to a full entropy balance at a later time in the chapter. Right now, we're just kind of building up our terms. Now, this term represents entropy transfer by heat, and this term represents entropy generation. Now, for first law analysis, we say that energy cannot be created or destroyed. But in the second law analysis, energy or entropy can be generated, right? And so what this does is that it helps us to analyze a process, being able to look at the total entropy change of a system and how much of that is equated to entropy generation. This term, entropy generation, Sgen, is always a positive quantity, and its value depends on the process. And it is not a property. Sgen is not a property. Sgen changes in value according to the irreversibility of a process. The more irreversible a process is, the greater value Sgen is. For an isolated system, meaning that nothing crosses the boundary, right? So, for example, a perfectly insulated system with a perfectly insulated closed system would be an isolated system. Tells me that the change in entropy is greater than or equal to 0. Please, let's take a minute again to review this because this can be confusing. What is this S2 minus S1? If I have a process going from state 1 to state 2, entropy, in this case here, this value of entropy is a property, right? So I can get my entropy at state 1, and I can get my entropy at state 2, and the change in entropy is going to be S2 minus S1, right? That would be the change in entropy for a process starting at state 1 and then going to state 2. That change in entropy is caused by many factors. That change in entropy can be caused by, let's say this is my system boundary. It can be caused by heat crossing the boundary, right? That carries with it an entropy. quantified as Q over T, that carries with it entropy, not entropy production, but the fact that heat flow has entropy in it. So I could have a process that occurs where the change in entropy is all equated to heat transfer, not irreversibilities by Sgen. But what I'm saying is for a closed system, for a system that has no mass crossing the boundary, I have entropy transfer to the system by heat and also entropy generation inside the system boundaries due to irreversibilities. So if my system is isolated, meaning that like nothing crosses the boundary, right? So there's no heat crossing the boundary. So if I have a change in entropy because I have a change in state from state 1 to state 2, this total change in entropy, S2 minus S1, this term goes away because there's no heat crossing the boundary, and so the only thing that can equate to the change in entropy in that case is entropy generation. It's very similar to some of the arguments that people use for, you know, the entropy of the universe is increasing. If you consider the universe to be an isolated system, nothing crossing the boundary into the universe from outside the universe, the change in entropy of the universe has to equal entropy generation. Right, because we know the entropy is increasing, and so the only reason it's increasing is because there's entropy being generation. So this equation can be expressed and verbalized as the total entropy of an isolated system during a process always increases, or in a limiting case, a reversible process remains constant. This is the increase in entropy principle. Now, the total entropy of a system, right, can be equal to the change in entropy of the subsystem. So let's say, you know, I have, I don't know, nitrogen, oxygen, carbon dioxide, all inside of a system, and I want to find a total change of entropy. Well, I can equate it to the change in entropy of nitrogen plus the change in entropy of CO2 plus the change in entropy of O2, as in this particular example. So a system in surroundings can be viewed as two subsystems as well of an isolated system. So if you're looking for the total change in entropy of a system, well, you can do that by looking at the change in entropy of the subsystems. So since no actual process is truly reversible, one can conclude that some entropy is always generated during a process. So the entropy of the universe, which can be considered an isolated system, is continuously increasing. The entropy change of a system can be the entropy change of a system can be negative, right? So let's go back, right? How can this be true? It's important to understand there's a difference between the change in entropy of a system and the entropy generation. They are not the same thing. They are one term in a whole entropy balance, right? We are looking at the fact that we have here the change in entropy of a closed system. This is for a closed system. The change in entropy of a closed system is equal to the entropy transfer by heat plus Sgen. So let's say I have a system that's giving up heat, right? If I have a system that's giving up heat and I have a positive value for Sgen, but the heat leaving the system is carrying it has a negative value because it's carrying entropy out of the system, and the change in entropy of the system, I'm sorry, the entropy generated in the system has a positive number, but the entropy being carried away by heat has a greater negative number. This can equate to a negative number. I can have this can happen, right? I can have a negative entropy change, but my entropy generation has to be positive. So in terms of Sgen has to be greater than 0 for an irreversible process, equal to 0 for a reversible process, and less than 0. Well, that's impossible. But delta S can be negative. Okay. The increase of entropy principle leads to the following conclusions. 1, processes can occur in a certain direction only. A process must occur in the direction of increasing entropy. A process must occur in a direction of increasing entropy, not in a direction of increasing delta entropy, but in a in a direction of increasing entropy. And entropy is not conserved. It's a non-conserved property, meaning there's no such thing as the conservation of entropy. Since entropy can be created, there's no such thing as a conservation of entropy because it's not conserved. Conserved and created, those two things don't go together. An entropy generation is a measure of the irreversibilities present during a process.